Anybody have any questions before we get started? Obviously, I got to get jumping to it since I started late. I think, if I remember correctly, I did go ahead and I made all the test and homework due dates. They should be correct for the rest of the semester. You'll notice I did add some extra chapters that are extra credit. You're completely open to doing them. So the way it works is basically every time I give you an extra credit assignment, I up the number of assignments, homework assignments that I drop as your lowest grades, increase that by 1. So for instance, if I added 1 extra homework assignment, instead of dropping 1 homework grade, like I think the syllabus says, I'll drop 2. So that's the way that works. No matter how big or small I make it, it basically counts as another homework assignment. So I think I've also made another test available to you. Make sure you write down in your calendar on your phone, ideally, so it reminds you 2 days in advance, say, and 2 hours in advance for you to make sure you take it. There'll be another one. I think we have 2 more tests before the final. So make sure you do that. Anybody have any questions before we get started? Last time we finished chapter 18, that was on kinetic theory and the ideal gas law. We're going to start making use of that in chapter 19. So this chapter is actually going to take 2 days at least. So I'm going to cover the first law and calorimetry and stuff like that on this day, and then I'll show you some of the cool things we can do with the ideal gas law after that. And I probably will spend a single day, maybe 2, depending on how much time we got, because really the excitement of this course for me, especially for students that have never had a 3-semester calculus-based physics sequence, you're supposed to have modern physics, so I get to cover quantum mechanics in this. So that's really what we're shooting for. The good news is if we don't get to quantum mechanics, that's okay, because a lot of places require you to take 3 semesters as opposed to 2. If you take 3 semesters and you have to take a 3rd one when you get somewhere else, then you already be up a little bit, because usually the 3rd semester starts with relativity, does quantum mechanics 1, which is basically early quantum theory, quantum of the atom, quantum of molecules, then it goes into nuclear physics and elementary particle physics, and usually often covered particle physics in 241 as well. So I've stalled long enough to see if anybody else is coming, but it looks like 7 is the number. It says there's 8 in here, but it counts me. So still no questions? All right. Well, heat and the first law of thermodynamics. So to begin with, there's a difference between, at least conceptually, at the time of James Prescott Joule and Clausius and some of these other famous people of the era, there was a distinct difference between heat and work and mechanical energy. Those were very, very different things. They had figured out that work could be done to increase mechanical energy. So for instance, you can, apply a force to an object to lift it. That force, if you take the integral of the force dot dl over the path that it travels, you will get the work done on that block. Now, if you take that work done on that block, you'll find out that that's exactly equal to m times g times h for that block, which is m the mass times g gravitational acceleration times h the actual height at which you lifted it, assuming air resistance was negligible. You weren't, for instance, curling it through, say, molasses or syrup or something. If that was the case, then you had a dissipative force. You had to take that into consideration, and so on and so forth. So people understood that work and mechanical energy were one and the same. What they didn't understand necessarily was that heat energy, and I'm using words that we use here in modern day science, but they understood the concept of heat, but it wasn't necessarily the same thing as energy to them, and it definitely wasn't mechanical energy. So James Prescott Joule did this really interesting experiment where he tried to see if they were related. In the experiment, you can see a picture of it in your textbook, or at least a simplified version of a experiment of it in your textbook. But if you imagine a little propeller, okay, a propeller on a rod, and you take that propeller on the rod and you submerge the propeller, or multiple propellers would be even better, and you stick that inside of what we call a calorimeter. A calorimeter is usually a very conductive material, like an aluminum cup, which has a high conductivity. An aluminum conductive cup containing water, and then that aluminum conductive cup is normally separated from something else that may or may not be conductive, but it's separated in such a way that there's a nice air gap, which we know is not very conductive, between it and whatever is holding that conductive cup. So normally what it is in a lab situation is you have an aluminum cup, then you have like a fiber, maybe it's fiberglass, maybe it is wool, maybe it's cardboard, maybe it's cardboard coated in wool, maybe it's cardboard coated in wool, coated in the blood of vampires. I don't know. Anyways, just trying to get your attention here. But anyways, if you take that wafer and that's like a little spacer that holds up the conductive aluminum cup and leaves a gap about this big all the way around the cup and above, below the cup, and away from the outer container. And in fact, our calorimeters are actually aluminum containers outside of the aluminum cup. And that's just fine, because we don't care if that outer cup gains heat or whatever. The main thing is we don't want the heat coming from the outside environment to contribute to the calorimeter cup itself, which is the aluminum cup inside where their water is. Okay. So you can then have, for instance, on top of that, maybe a plastic lid. Plastic's actually pretty conductive, but you can have, for instance, a coat of styrofoam on the inside of the plastic lid, maybe a few small holes where very little air will flow. But by having that wafer around, which is really like a big washer around, you're not allowing air currents to flow. You're not allowing the aluminum of, as I told you, the outer cup of the calorimeter is also aluminum, and the calorimeter cup's aluminum. You're not allowing the heat flowing through that outer aluminum cup to touch, therefore conduction's out of the question. It can't touch the aluminum cup inside. And that wafer, which is made, like I said, cardboard covered in wool or something like that, that is a very non-conductive material, and it literally only touches along that little edge, and then there's a little lip on the inner cup. So the amount of contact it has with the wafer is very thin. It's usually about maybe 1/8 of an inch or even thinner, thick. And of course, it would be equal to the circumference of the innermost circumference of that aluminum calorimeter cup. And that's the entire surface area in contact. So spacing it out like that holds it up, but also doesn't allow conduction, but also it makes it really impossible for convection to occur. Convection being where basically something hot could heat air immediately above it, and then that air being hotter now has a lower density and therefore expands. Because it expands, it rises and then delivers that warmth or that energy, that heat, to the object. That can't happen. There's no real flow going around there. And in fact, that makes a fairly efficient, what we call calorimeter. Again, you can use a lid with a hole in it, because you will need, of course, the pin with the propeller blades to go inside. You'll also need a hole for a thermometer to go inside. And ideally, you'd like the thermometer's mass. You going for today, baby? All right, love you. Drive carefully. Text me when you make it home. That's my youngest big girl, who's now a driver, and she's leaving me forever, I think. And anyways, not really. She's just going to be back probably tomorrow. Anyways, so that thermometer should be fairly small mass compared to the mass of the water and all the stuff we're studying. Because obviously it's going to come in with a temperature of, say, room temperature, and if it contributes much heat to the water, then I've screwed the experiment up. but luckily it's usually not that big of a deal. We usually have much more water, and water, by the way, has a high specific heat, so it's a really ideal thing to work calorimetry in. So you now have this picture of a cup that is conductive, and of course we know its mass. And if we want to measure the temperature of the container and everything, what we do is we measure the temperature of the water. The water will reach equilibrium with the thermometer, and we'll know that because the thermometer will probably, since the water is usually colder than room temperature, will probably drop, and then come to a stop. Once it comes to a stop, that means it's reached equilibrium with the temperature of the water. All right, in other words, it's reached thermal equilibrium with the water itself. And by the way, if the cup isn't at the same temperature as the water, then that thermometer will continue to change, because the water is constantly changing temperature until it's the same temperature as the cup. So by knowing the mass of the cup, what it's made out of, you can account for any heat it may gain as well. So that's what a calorimeter is. It's like a really fancy 2-layered thermos or cooler, okay? So now we have this calorimeter, we have this lid, we have this propeller spindle that's going down inside of the liquid. And what we're gonna do is we're gonna have a spool on the propeller shaft that's gonna have a buttload of string wrapped around it. That buttload of string is going to run over to a pulley that just transfers basically force from going to the right to going down, okay? And we put a mass on there, a known mass, M, and we hang it and allow it to fall through a distance h. That's the James Prescott Joule experiment. So what you're doing is you're taking potential energy, mgh, allowing all that potential energy to be delivered to the water via spinning of a blade. Now, in that process, we watch the thermometer. It's a lot easier, even with all this description, it's a lot easier said than done. We watch this process, and we watch this thermometer go up, 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 up. And I say up, 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 I mean up that much, okay? Even with a really good thermometer, it's not going to go up a whole lot. But what you ultimately see is that eventually the temperature of the water, the blade, the calorimeter cup, whose mass we know, that all comes to an equilibrium. So the temperature is now set, and then you do the spinning experiment. So you allow the object to fall, and then you wait, because what's happened here is you've made a swirl in the water. And a swirl is good, but a swirl is a very organized rotation of molecules around the inside surface. And temperature is a measure of the average translational kinetic energy of the molecules or atoms of the substance. So what we've got to wait for is that energy that was all sort of organized to distribute itself throughout the water, so that now we don't necessarily see any more spinning occurring, but what we do see is a net average change in the kinetic energy, specifically translational kinetic energy of the molecules or atoms of the water, okay? That will be registered by a change in temperature, okay? Once that temperature reaches its highest point, we record it. Of course, we keep recording it just in case that one happened to be the highest temperature. And eventually it'll reach a max and then start to fall back down, because now the calorimeter, though close to perfect, is not perfect. It's going to give off some of its heat to the surroundings, or it might actually rise back up because maybe the surroundings are actually hotter than the water in the cup or whatever. Ideally, you'd want it a little cooler than the water in the cup. Now, once that was done, we got not what's normally viewed as a unit conversion, which is what we did get, but we got also, in addition to that unit conversion, we got a whole new paradigm of thinking. We got the idea that this mechanical work, that long, boring talk that I just gave you, this mechanical work of an object falling through a distance h, is exactly equivalent in some sense to heat. And Let me turn on my document cam so you can see this magnificent, wonderful, great, awesome discovery. Okay, here's the magnificent, great, awesome discovery. And I really mean that, by the way. It was a monumentally big deal. What we found was that 4.186, and I used to call this 4.184 for some reason. So I don't know if science changed or if I was just an idiot for the first several years, but 4.186 joules turns out to be equal to exactly 1 calorie. Okay. Calorie, by the way, was the unit that we used for heat. For instance, 1 calorie is defined to be the amount of heat required to raise the temperature of 1.00, as many decimal places as we could, grams of water from, here's a very specific part, 14.5 degrees Celsius to 15.5 degrees Celsius. Now, it does change from temperature to temperature, but as your book points out, over a range of 0 degrees Celsius to 100 degrees Celsius, the change is less than 1%. So we're okay using 1 calorie per gram per Celsius degree for this unit. Okay. So that is what a calorie is. It's the amount of heat required to raise the temperature of 1 gram of water, specifically from 14.5 degrees Celsius to 15.5 degrees Celsius. But you can assume that that's the amount required to move, to change any gram of water by a temperature of 1 degree Celsius. Okay. Now, it also happens to be that 1 kcal, that's a kilocalorie, which is also defined to be 1. Notice the difference here. I wrote a capital Cal, a capital C. That's defined to be the amount of heat required to raise the temperature of 1.000. I'll put a bar over that too, so you can say we're pretending that it's an infinite number of decimal places. Kilogram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Okay. Now, has anybody ever heard of another unit of energy other than a calorie or a joule? And watch out, it's really easy to accidentally think something's energy and it turns out to be power. Power is energy per time. Does anybody recall anything? Anybody in here working heat and air?
Something that starts with the letter B in the British system.
Exactly, the BTU. Okay, 1 BTU is equal to 1 British thermal unit. Okay, 1 BTU is defined to be the amount of heat required to raise, and your book says this as well, so you need not necessarily write it, but it's actually the amount of energy required to raise I want to say it's a whole gallon, but let me double check. It's either a gallon or a pound. I think it was a pound, maybe. British Thermodynamics. Yeah, that's it. To raise 1.00, I'll put a bar after that as well, pound of water by, and I don't know that it's exactly 14.5 to 15.5 like we are here. So I'm just going to say by 1 degree Celsius. So I'll say 1 Celsius degree. Remember, when we put the degree afterwards, we mean a change in temperature. Whereas when we put a degree before, we mean an actual temperature. Okay. So that's what the British thermal unit is. And it turns out that a British thermal unit is actually related to a actual calorie by a very specific amount. It's not one that we use that often, but basically 1 BTU is equal to 0.22 or 252. So I should remember that easily enough. 252 kilocalories, which is equal to 1,056 joules. Okay. Area code here in my part of North Carolina is 252. So y'all's is 757. This is 252. There's also another unit, and that is 4.186 kilojoules is equal to 1 kcal, which, as I said, was 1 calorie. Anybody want to guess which one of those calories is the calorie we talk about when we're talking about Twinkies and whatnot?
The kilocalorie is the one used in food.
That's exactly right. So yeah, if you ever want to think about, hey, I really like cheesecake, I'm going to eat some cheesecake, eat your cheesecake. That's just fine. Okay. We don't have to have abs. We don't have to be perfectly flat stomach, but we do need to be somewhat healthy. So if you're suffering of diabetes, maybe not eat the whole cheesecake, right? Or, or if you're having heart issues, maybe not eat the whole cheesecake, but be advised, there's not an exercise you're going to do to make up for that slice of cheesecake, because not only is a calorie hard to burn, you're not even burning a calorie, you're burning a kilocalorie. Okay. So actually, I think I did a calculation one time, even running a marathon would not make up for the 350 calories that I think a Twinkie was. So that's something you can do on your own calculations. You'll see there's problems like that in the end of the chapter. I want to say there's one in the homework as well. The main thing is, yeah, that's not going to happen. Okay. But neatly, a friend of mine went on a diet. This is back before even Atkins wrote his book or anything. But my dad, who maybe is a little Sheldon-esque in that he's, pretty much says what he thinks sometimes without actually thinking. Okay. Saw a friend of ours. His name was Bruce, a good family friend. His sister is my mom's best friend. His kids were like my cousins, that sort of thing. That was all cool. But anyways, we hadn't seen him in a couple years, and we go to Christmas party, and there he was. And my dad tells him, "Hey, Bruce, looks like you put on a little bit of weight there." He's like, "What?" He said, "Yeah, look like you buttered right up there." Didn't think anything of it. Well, evidently that bothered Bruce quite a bit, so he went on a diet. His diet consisted of, I'm going to eat a steak. I'm going to, believe it or not, he actually kept up the beer too. I'm going to drink beer, and I'm going to eat ice water, or eat ice and drink water all day. And that's all I'm going to do. So literally that was his diet. And within a year, I kid you not, he was as ripped up as anybody I've ever seen in bodybuilding. He had ripped up abs. This dude was like, he had to be 49, 50 at the time. Ripped up abs, ripped up pecs, ripped up quads, and he didn't skip leg day like a lot of us do. But the cool part of the story is just eating ice chips, just eating ice. When you actually eat ice, ice has a high specific heat. The specific heat the specific heat of water is 1 calorie per gram per degree Celsius. Okay. A gram is a very small amount of weight. A kilocalorie would be a kilogram. A kilogram, of course, is about 2.2 pounds. If you drank 2.2 pounds of water, you've got to take that water from whatever temperature it was and bring it up to your body temperature. And that requires you to burn calories. If you happen to eat ice, you're burning calories in chewing it. If you happen to eat ice that's below 0 degrees Celsius, which is quite often the case, you have to bring the ice up to a temperature of 0 degrees Celsius. You have to break it, which burns calories. Then you have to bring that ice that is now water, which actually has a smaller volume as water than it did as ice, so it doesn't feel so filling in your stomach. And now you have to bring that up to body temperature as well. So that is actually a fairly, well, cut out the beer and maybe throw some veggies in there or something, but or at least a multivitamin, and that's a pretty good diet. So anyways, that's what I'll leave you with regarding that stuff. Anybody have any questions on that? Okay, so this is a monumentally fundamental discovery. Yes, it's a unit conversion. Okay, that's true. It's a unit conversion, but it's also a fundamental different way of thinking. It says that, in fact, calories, which we associate with heat, is equivalent to mechanical energy. Potential energy, kinetic energy, 1/2 mv squared, 1/2 I omega squared, all that good stuff. So keep that in mind. Now, with that idea, what I want to introduce next to you is the concept of internal energy and specific heat. So it turns out internal energy, which your book is using E for, so let's call this internal energy. That's my danger dog. His name's Cosmo, 4 pounds of fury. You've probably seen him on my YouTube channel. But internal energy, your book is calling E sub internal. And really what it's defined to be is for a given substance, if you take the N atoms / molecules that make up that particular sample of space, or that item that we choose to study, that N times the average kinetic energy is the internal energy. Okay. Now notice that's 1/2 mv squared. That's actually the internal energy. And in this case, well, if you read it, it says, let us calculate the internal energy of N moles of an ideal monatomic gas. So this said ideal, it said monatomic gas. Okay. Monatomic means the molecules are made of a single atom. Okay. Now you can bicker and say O2 because that's, you know, a single atom in terms of variety, but really we really like to think of just plain O as opposed to O2, or maybe just plain HE, because we know that doesn't bond with another HE to make its normal scenario. The reason being is because of the extra degrees of freedom that O2 gives you. O2 has a center of mass that moves with a velocity v. It can move in the left-right direction, it can move in the up-down direction, it can move in the in-out direction. That's 3 of those, and that's why we got that 3/2 kT from last time. However, when you have a diatomic molecule like oxygen, okay, then that actually has an additional number of degrees of freedom. It's a dumbbell basically, so you can look at it like this and this, and every type of energy that can be represented as something times something squared is another degree of freedom. So we can rotate about this axis, excuse me, we can rotate this barbell about this axis. That's another degree of freedom. We can rotate this barbell about not this axis because that's sort of in the same plane, but we can rotate it about, let's say, the axis coming out of the plane. So we can rotate it about this axis, in which case it's spinning this way. Now, in principle, you can rotate it about that axis, but it's an atom. So those are such small objects, it's not really not a relevant amount of energy. So I've got 2 degrees of freedom just because this is now a barbell shaped molecule instead of a single dot molecule. That's just as a result of rotation. But now you also have the ability for this to vibrate in and out. This one can vibrate, so that's a 1/2 kx squared. This one can vibrate, so you've got extra degrees of freedom. The internal energy really is made up of all the degrees of freedom. So it's not just 1/2 mv squared, it's all those different types of energy. So that's what I was wanting to warn you about. Now, using the fact that kinetic energy is 3/2 kT, we can say the internal energy of a monatomic ideal gas, E internal, is actually equal to 3/2 N, where N is the number of molecules or atoms, kT. So this is number of molecules. And actually, remember, I'm saying molecules, but really it's a monatomic gas, so it's really atoms. Okay, so it's actually atoms, just in this formula. Okay, the idea of internal energy being N times the number of degrees of freedom, which is what goes here, times 1/2 kT, that's the more general result of any ideal gas. Okay, so that's why I'm trying to split hairs a little bit here, but that's what internal energy is. And if you think about it, you can also use the fact that, remember, PV, I'm using all caps here, where I did advise you to look up the difference between extrinsic and intrinsic variables. So I'm still asking you to do that, so you'll understand why some are uppercase and some are lowercase, but still look those words up. But I'm doing all uppercase now. We did learn that PV equals nRT, and then we also learned that PV is equal to N times Boltzmann constant times time. So you can see now that another version of the internal energy for an ideal monatomic gas is 3/2 nRT. Notice this time it's lowercase n times r times t. Okay, so this is one of those rare occasions where we actually can have a formula for something that's important. That's the internal energy. Now, what matters in terms of whether energy flows or heat flows, that's really what heat is. Heat is energy in flow. Okay, so that's a key idea that you need to understand. Heat is energy flowing from one object to another. What dictates whether heat flows from one object to another is heat always flows from a warm body to a colder body that it's actually touching. So that's conduction or convection. Radiation, same thing applies. Radiation radiates out from a source of energy and goes to a source of lower temperature. Okay, but it can actually, it can also radiate the other way around. So for instance, when you walk into a gym that's initially, let's say, a nice cool 68 degrees Fahrenheit, you come in, and if you do the actual calculation, which is something called the Stephon Boltzmann Law, I'll write that here, you'll run into that a little bit later. The Stephon Boltzmann, that's the F there, Stephon Boltzmann Law. What you will discover is that you radiate as a result of your surface area, which is one of the parameters, and your temperature of your surface area. You radiate out at a rate proportional to the 4th power of your temperature. So that being said, the room re-radiates back into you a temperature related to the surface area at contact with you, which again is the same as your surface area, at a rate of its temperature to the force. So you're not losing all your energy, you're just losing sort of the excess energy due to the excess temperature. So if you do that calculation, what you'll find is that a human in a room at about room temperature is equivalent to a 100-watt light bulb. Okay, so when you walk into a gym that is 68 degrees Fahrenheit, it stays 68 degrees Fahrenheit. And when your wife, your daughter, your son, or whatever comes in, that brings it up another 200, 300 watts. But once you get that auditorium or gym filled up, you've got thousands or at least hundreds of watts of energy, and then slowly it warms up. Okay, that warming up, that energy leaving you is actually increasing the internal energy of the air in the room. That internal energy has a bunch of different ways that energy is going to be distributed. It's going to be distributed in moving your atoms and molecules at a higher rate left and right. That contributes to the temperature. It's going to contribute to the atoms and molecules in the air moving in an increased velocity in the up-down direction. That's another one that contributes to temperature. It's going to increase the average velocity of your atoms and molecules of the air in the room by having them increase their average speed moving in and out. That's the third dimension. Now, the problem is, if they're these, then you actually have a couple more degrees of freedom that energy can go to, and they don't change the temperature at all. And if you have, for instance, water, which you obviously do, there's always water vapor in the air, which is a Mickey Mouse type atom or molecule, excuse me. Okay. Then you've got the ability to rotate about that axis perpendicular to the page, right through Mickey's face. You've got a ability to rotate about an axis perpendicular or parallel to the page, basically, but perpendicular to the last one, so it can rotate that way. You've got vibrations along here and here. Those are a lot of different modes of vibration that go into things other than temperature. The only thing that goes into temperature is this Mickey Mouse head moving left, right, up, down, or in, out. All the other ones are extras. That's why water specifically has a high specific heat, because it's got a lot of modes of energy that it can go into. And the Equipetition Theorem, here's that word, EQUAPARTITION. God, I hope I spelled that right. Theorem. It's sort of related to the law of large numbers, which basically says, hey, when you're talking molecules and atoms, even that small water bottle that is like this tall, even that has 1 followed by 23 zeros atoms in it. Okay. Now, if you spew 100 billion joules of energy into those 10 to the 23rd atoms or molecules, the Equipetition Theorem says every degree of freedom gets exactly the same amount of energy. So if you're heating up a monatomic gas, all the energy goes into heating up, i.e. changing the temperature of the gas. If you're heating up water molecules, 3 of them go into changing the temperature of the water, but we've seen at least 1, 2, 3, 4. There's probably, I think it's 9 different degrees of freedom for the water molecule, and only 3 of those raise temperature. That's why, again, water is a great insulator. It has a lot of ways of taking in heat that don't involve changing temperature. Okay. So I think I've beat that horse to death at this point. So I apologize for the violent sounding metaphors, but anyways, that's what happens. If this would have been in the 50s, I always would have been talking about nuclear war or something. So I guess we're always going to do something violent when it comes to physics. But anyways, so that's what internal energy is. And that's an important thing to understand. But by talking about it, we've brought up the concept of specific heat. So here's the concept of specific heat. And specific heat is given the symbol C, and sometimes you'll see it capital C, but there's a difference. This is another one of those extrinsic versus intrinsic variables, okay? But if you think about it this way, you say, okay, hey, I want to know what causes something to change temperature. Remember, our symbol for change is delta. That's always the triangle with the point on top. That's the delta. And of course, it always means T final minus T initial, except this very lecture, I'm going to start teaching you to ignore that, at least when you're solving calorimetry problems, okay? But generally speaking, if you open up a book and you see something that says delta something, that delta means final minus initial, unless you find in a very nearby paragraph it's saying, hey, by the way, we're not going to treat it that way, because every other book in the world, every other chapter in the world, every other everything in the world says delta is final minus initial. So if you start thinking about that, would you think that it's easier to make a big change in temperature for a small mass or for a large mass? In other words, is it easier to change the temperature of a gram of lead or 1,400 kilograms of lead? Which one's easier? Yes, the small mass, says Makita and Gavin. That's correct. So what that tells you is the change in temperature is directly proportional to the mass, right? And you also say, later on, we'll find another way of expressing it. You could also say it's directly proportional to the number of moles. That's what the N means, but either one of those are acceptable, okay? So there's molar specific heat, and that's in terms of N, and then there's regular specific heat in terms of mass. So I'm already going to say it depends on mass, okay? Would you say it's directly proportional, thumbs up, or inversely proportional, thumbs up, thumbs down, to the amount of heat you add? So for instance, if you're wanting to increase the temperature of that, let's say, kilogram of lead, will you increase it more by adding 100 joules, or would you increase it more by adding 4 joules? Waiting for at least Makita or Gavin to draw. Yes, exactly. You'd expect it to be directly. In other words, the amount of heat you add, which we use the symbol Q for, is directly proportional to the change in temperature. Okay. So guess what? It turns out that the formula you ultimately can get from this is the amount of heat added to a substance is actually equal to, and I said this a little weird writing here, so that's why I switched and started doing this. The amount of heat added is directly proportional to the mass and directly proportional to the change in temperature, which is what we're thinking, right? A large temperature change occurs for a small amount of mass, and a small temperature occurs for a large amount of mass, right? And then they treat the constant of proportionality as something called C, the specific heat. Now, I think all the words I said, even though I was writing it in a weird way, I think all the words I said was right, but I think you understand that, oh, yeah, this should have been written like this. That's the main thing, because obviously when y'all said a smaller mass changes the temperature more, that would have been what we call inversely proportional to. Y'all answered the right questions. I think I said all the right words, but I wrote it backwards because I don't know, I'm a crackhead. Okay. I'm not really a crackhead, by the way. I'm just being funny. And I apologize for anybody that has anybody suffering from the addictions of crack and stuff. I know that's bad. All right. Anyways, so what we find out is, in fact, once you add an amount of heat Q to a substance, that Q is going to cause a change in temperature. That change in temperature is, of course, smaller if the mass is really big, but bigger if the mass is really small. That thing that dictates when you're comparing two of the same masses, let's say a kilogram of wool to a kilogram of iron, if you put 100 joules of heat to a kilogram of iron, you're going to get a really high change in temperature. If you put 100 joules of heat to a kilogram of wool, you're going to get a very small change in temperature. And it turns out that that is because the specific heat of wool, which you probably can't even look up, is considerably larger than the specific heat of iron. So that's our ultimate formula for changing temperature. Heat added is equal to MC delta T. And it's only added, by the way, if you want to change in temperature. Okay, so what does that mean? That means if you wish to cool down your tea, let's say you're like me, I'm a Southerner, I drink iced tea. And I really like to drink iced tea, which is what they mean when they say iced tea. They really mean tea that's at 0 degrees Celsius. That's really the best of teas. We'll talk about that a little bit later. But let's imagine we have, well, you probably have realized it nowadays, but basically a 16-ounce drink is about 500 milliliters. So we're going to say we have, here's an example. That'll be example 1. So we have 500 milliliters of tea, which is essentially water. If you've ever made tea, you know it's like 1 to 4 little tea bags of tea, and you boil that in a pot of water, and then you mix it with a gallon of water, and that makes like a gallon of tea. And not only that, the tea bags, when you pull them out, they're still soaking wet, and the majority of the mass is still there. So you've at best tinted the water with tea. Okay, so 500 milliliters of tea at, let's say you just finished boiling it, so it's kind of warm. Let's say it's at 90.0, and I'm going to call that 500 points. So we have 3 sig figs, 90 degrees Celsius. Okay, and we decide to water it down. I'm using water instead of ice for a reason. I've got to introduce another equation before I can use ice. Okay, I decide to water it down because it's bitter. I'm going to water it down by adding, let's say, by adding 100.0 milliliters of water. And y'all happen to know what this temperature is because y'all listened to my goofy little poem, at 10.0 degrees Celsius. Anybody remember what that temperature is? Okay. Remember, 30 is hot, 20 is nice, 10 is cold, 0 is ice. And in fact, we discovered 0 was 32 degrees Fahrenheit. And if you go up by 10, you have to go up by 18. So 32 plus 18 gives you 50. So this is 50 degrees Celsius compared to 90 degrees Celsius. Okay. So here's a calorimetry problem, and that's what it's called, calorimetry. And your book and many other books will tell you that when you're using a calorimetry problem, you say delta Q is equal to 0, and that's exactly right. Okay, that will work. But here's the problem: you've got to keep in your mind exactly what is a negative heat and what is a positive heat. For instance, when you go from let's say from a liquid state to a solid state, is that a loss in heat or is that a gain in heat? Because one's got to be negative and the other one's got to be positive. I know that traditionally my students have had a little bit of difficulty thinking about going from liquid to solid, or from gas to liquid, or from solid to liquid, or from liquid to gas. So what I do is I say heat added equals heat lost. Okay. In other words, I normally just say Q added equals Q lost. And what that does is just automatically makes everything come out positive. And that's why I was telling you, I'm not going to pay attention to delta being final minus initial. I'm just going to make sure all my terms are positive. So in this case, can anybody tell me what is losing heat and what is gaining heat? Is the T losing heat, or is the water losing heat? And I say losing heat, I'm really meaning losing energy. It's actually giving heat, if you will, because the heat is the transfer part, not the thing that it contains. You can't contain heat.
The T is losing.
Exactly. So the lost is the T, and the gained is the water. That's the value of this. Everybody knows that. I mean, you're the one that spoke up, but I suspect everyone knew it. So what I'm going to do is I'm going to use the same formula. Q is equal to MC delta T. And I happen to know, by the way, that water and T are both essentially water. So the density of H2O is in fact 1 kilogram per liter. Okay, that's another helpful unit. It's also 1,000 kilograms per cubic meter, and it's also 1 gram per cubic centimeter, and it's also 1 gram per milliliter. Those are all densities of water that I happen to know, and everybody should know, really, just because it's such an easy number to deal with. So I'm going to say heat added equals heat lost. So this side's going to be the water. And what I'm going to say is the water was 100 milliliters, which I can see is clearly 100 grams. So I'm going to say 100.0 grams of water times the specific heat of water, which I told you 1 calorie is defined to be the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. So what I'm going to say is that specific heat, C, is 1 calorie per gram per, notice I write the degree after the Celsius. Okay. And I know the water, which was at 10 degrees Celsius, is going to be at a higher temperature. So I'm going to ignore the delta being final minus initial, and I'm just going to make sure it's positive. So the final temperature of the water is in fact going to be higher than the initial temperature. So I'm going to say T final minus, in fact, 10.0 Celsius, degrees Celsius. Okay. On the other side, I have 500 milliliters, which of course is 500 grams. the specific heat of tea is essentially the same thing as the specific heat of water. So that's 1 calorie per gram Celsius degree. Now, in this case, the water is actually cooling down. I mean, the tea is actually cooling down. So this is the tea side over here. So it's cooling down. So that means its initial temperature is higher. So what I want to do is I want to write 90.0 degrees Celsius minus T final. Okay. That way, notice they're both positive. So that's the only difference between that and using it as delta Q equals 0. You'll see that it's not, there's no real reason, if you will, for it until we get to changing of states, which is the next part. So if I do this math, I see that I get 100 T final and I get minus 500 T final. So if I pull this over here, that'll be 600 T final. And now I've got, that's just my T final part. Now I've got 100 times 1 again, minus 10. I'm going to pull that to the other side. That's going to make it become, positive. So 100 times 10 gives me 1,000. And of course, the grams and the calories canceled out. So now I'm left with 1,000 calories. So I'll say 1,000, and that's actually to the proper number of sig figs calories. And on this side over here, I've got 5,000 grams times 1 calorie per gram. That leaves a calorie per Celsius degree, but then times 90. And of course, 5 times 90 is 45,000, but this is going to have to be 450,000. So that's plus 450,000 calories. So I can now say finally that, and I'm sorry for writing in such a small area here, but I didn't want to change a whole nother sheet of paper for just that. So what I'm looking at is basically 450,000, 451,000 divided by 600. So 451,000 divided by 600 should give me my final temperature. And that clearly is not right because I did something wrong. Oh, 500 times 1. I think I read that as 5,000. That might have been the problem. Yep, stupid me. I read that as 5,000. I apologize. That's 500. Stupid me. Okay, so that's 500 times 90. That's a lot smaller number. That's 45,000, which is a lot better. Okay, so that's 45,000 plus 1,000 is equal to 46,000. And now I'm going to divide that by 600. And that's going to give me 75.6. That makes much more sense. So I get 75.6 or 76.6. So the final temperature, not really that pleasant, is it? It went from 90 to 76. That's friggin' 80-degree T. That sucks, right? So anyways, that's a typical calorimeter problem. And that's the way I recommend you do it. Just think of everything that's losing heat and then think of everything that's gaining heat. Make sure all those terms are positive and set them equal to each other, add it up. Okay, so you add up all the things that are having heat added to them, and you set that equal to the sum of all the things that are losing heat, and then you've done a calorimetry problem. Any questions on that? All right, so the next issue is, and by the way, your book has a table of specific heats on page 499. So I'll just write that right here. Table. That's what you use when you're doing the homework, by the way. On page 499, which is table 19.1. the main thing you can see there is they've got it in calories per gram Celsius degree. They've got it in kilocalories per kilogram Celsius degree. And they've also got it in joules per kilogram Celsius degree. And to give you some appreciation for how much and how good of an insulator water is, water has a specific heat, like I said, of 1, liquid water that is. That's 4,186 joules per calorie. I mean, joules per kilogram degrees Celsius. Let me write that down here. CH2O equals 1.00 calories per gram Celsius degree, or get this, 4,186 joules per kilogram Celsius degree. Notice the difference is kilograms down here. That makes a big difference. Okay, so that's why it became such a big number. Aluminum, on the other hand, has 0.2. So C for aluminum is 0.22. For copper is even worse. So C for copper is 0.093. And these are all calories per gram Celsius degree, calorie per gram Celsius degree. So you can see really specific heats of metals is extremely low, but that's good. That's why we make our cookware out of metal. I mean, we wouldn't want it to take a long time to heat things up. All right. So now that we got that, I'm going to have to give you a little bit of an idea. And your book does start to talk about that on page 499, the different modes or different freedoms that you have, degrees of freedom that you have when dealing with polyatomic molecules as opposed to just monatomic ideal gas losses. So I've already done the calorimetry section, that's section 19.4. What I want to show you next is a nice graph of temperature versus heat added. And let's do it, say, just for, I don't know, ice, okay? So this is sort of like what your book is doing on page 502, but better because I'm doing it. Just being funny. All right, so what we're looking at here is the temperature in degrees Celsius. Remember, never make a graph that doesn't have the axes labeled and that doesn't have the units marked. And this, of course, right here is heat added. So this is Q added. And it's actually Q added in kilocalories. Okay. So if you start from 0 degrees Celsius, okay, it turns out that water has a very unique property specifically, or actually let's start from negative 40 degrees Celsius. That's what I'll do. Negative 40, I'll make this next half a line negative 20 and make this, so that's 20 there and that's 20 there. So that should be 0 degrees right there. And then the next one will be 20 and the next one will be 40. And the next one will be 60. Oh, no, that'd be 20 again. Yeah, 60. And then that'd be 80. And then that would be 100. Maybe a little smaller than I needed, but the main point is I've got it. So it turns out that if you add heat up to about 20 kilocalories, then what'll happen is you'll bring water up at a more or less uniform slope. In other words, that slope, notice, is degrees Celsius per Q. So that's something you can relate, if you will, to the specific heat of the substance. So this is all ice right here. So I'll say heat added to water. Okay, it started as ice, but here's the weird part. Once you get it up to 0 degrees Celsius, that's not all. It doesn't just immediately become water, because you've got to actually give it enough energy And I wrote ice there and it doesn't look like ice. Let me write it again. You've got to give it enough energy so that the molecules are separated by far enough distance that they're not clinging to each other like they were in the lattice, pseudo lattice that ice has. So in fact, it turns out you have to add another 80 kcals to that. So that's 20, 40, 60, 80. So it turns out your water in the ice form is just going to stay at 0 degrees Celsius all that time. Okay. So this is in fact a mixture of water and ice. And in fact, it differs based on temperature, based on pressure and stuff like that. But generally speaking, it takes additional. Actually, I said additional 80, so that should have been 100, not 80. So in other words, it takes an additional 80 kilocalories to convert that ice at 0 degrees Celsius to water. In other words, that's the latent heat of fusion. That's what they call it, the heat of fusion. Now, at that point, water can rather quickly rise up to, warm enough to actually become steam. Okay, so so we're going to actually raise the temperature now to allow it to start boiling. So here's the 100 degrees Celsius mark right about the middle of this line. And here's the 200 mark, because it's going to take about 200 more calories to take this kilogram of water. By the way, this is 1 kilogram of water. So it's going to take about that much more to get it to boiling. So at this point, it's water and it's all liquid. In other words, there might be a little bit of vapor pressure above it, but not very much. It's essentially all water. But here's the problem, and this is a big problem, because I've got to take this graph and I got to put a slot in it. You know what you do, you know how you do that with graphs that says, hey, I'm pretending this distance isn't very far, but oh my God, it's a buttload of distance here. And in fact, I'm going to go all the way from 200 to 740 kilocalories. So in other words, this distance from here to here is 540 kcal, whereas this distance from here to here is 80 kcal. Now, what happens at that point is basically I've added enough heat to keep the water at 100 degrees Celsius, but some of the water has fast enough molecules where they'll escape off into the air, but the rest of them, they got nothing. They're just staying in the liquid form and will in fact remain 100 degrees Celsius until they escape. So that's one of the reasons we use boiling water to cook with. We need our meats, for instance, to keep us from, getting trichinomosis or something horrible like that. We need our meats to reach an internal temperature of, X degrees. Well, that X degrees is almost always less than 212 degrees Fahrenheit, which is 100 degrees Celsius. So if you take meat and throw it in a vat of water and you boil the water, once that water reaches 100 degrees Celsius, it's going to stay 100 degrees Celsius until it all boils away. So if no matter how thick that chunk of meat is, eventually its entirety will reach equilibrium with the water that is boiling, and therefore will reach 212 degrees Celsius. And of course, will be safe to eat, unless you, picked up some roadkill, because that was pretty funky to begin with. Right. So during this state, you basically have water and steam. because as I said, there's a little bit of vapor pressure where the fastest of molecules can escape. And then, of course, this temperature goes up and up and up and up like that. And all you have at this point is just pure steam. But that's the way, not only that water behaves, that's the way everything behaves. So as you add heat, things warm up, 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 reach a critical temperature where they change from the solid state to starting to change to the liquid state, but they lock themselves in at that temperature. Again, that's another reason why we use ice to hold food, because we know ice, as long as it's frozen, is at 0 degrees Celsius at least. That's 32 degrees Fahrenheit. So all the meat in the freezer, as long as the freezer ice is still frozen, all the meat in the freezer is in a 32-degree environment and will eventually reach 32 degrees Fahrenheit. But if you keep adding heat, you're not going to change the temperature. You're not going to change the temperature. You're not going to change the temperature. You're not going to change the temperature until you've added an additional 80 kilocalories. Once you've added an additional 80 kilocalories, you've given it enough energy to break the bonds that were holding the water molecules in that pseudo lattice that ice has. At that point, the more heat you add, the hotter it gets, 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 the hotter it gets. But once it reaches that 100 degrees Celsius, and of course, at low pressures, that's a lower temperatures. At high pressures, that's a higher temperature. In fact, that's the way they, used to figure out, for instance, the source of the Nile. One of the big mysteries in the late 1800s, I think early 1900s, was what is the source of the Nile? And the Nile is a long river, and it actually is a weird one in that it runs north. So what you have to do is follow along the Nile as far as you can and try to look for a big body of water. And the body of water that has the lowest boiling point is the one at the highest altitude, because that's the one with the lowest pressure. So at low pressures, of course, the boiling point is not 100, but at 1 atmosphere, it's 100. So once you've added enough heat at 1 atmosphere, you reach 100 degrees Celsius and the water begins to boil. So it boils and boils and boils and boils. And remember, it's a lot bigger gap than we're showing here. I showed you as if it's this little short itty bitty gap, but in fact, it's a really, really big gap. It's a gap of some 540 kilocalories. In that case, you're actually trying to give the molecules and atoms, in the case of water, it's molecules, enough kinetic energy that they can break the attraction they have for one another by, remember, as a liquid, they're just sort of rolling on top of each other like ball bearings in a box. But they still have an attraction and an affinity for each other. Once you put in 540 kilocalories for that 1 kilogram of water, what's happened now is the average distance between them is only order of more than 10 times their own diameter or their own width across. And they break up and no longer are a lattice. Then if you add heat, they just get hotter and hotter and hotter in the steam form. So that's it. And it turns out those formulas are just Q equals M times L, where L can be heat of fusion. This is heat of vaporization. And that's it. We're done. You guys are free to go. We've covered up through section 19.5. And I'll wait for the last person to leave. Anybody have any questions?
I had one question on one of the previous homeworks, but it was one of them that was due like last Saturday, but I couldn't figure out one. I don't know. It's how to figure out the phase angle between the source voltage and each of the consecutive
parts.
junction. Yeah,
Right.
the sections. Mhm.
Okay. So remember, with regards to phase angle, what we look at is, just imagine this is in space. This is the voltage for the source, but it's also the voltage for the resistor. Okay. Now, Eli the Iceman says that the voltage is ahead of the current, which is this thing, in an inductor. So that amount right there is 90 degrees for the inductor. Now that inductance, remember, it actually becomes basically for a really, really, really low resistance, it just becomes a wire. And its resistance essentially goes to 0. So the XL, which is the inductive reactance, is in fact omega times L. Similarly, back here, we have the capacitor, and that's the Iceman, and that means the current follows the voltage by 90 degrees in a capacitor. So this is 90 degrees as well. And in fact, the XC is equal to 1 over omega C. As it turns out, as the frequency goes to infinity, the capacitance just looks like a straight piece of wire. So if they're ever asking you, hey, how much does the voltage lag for a capacitor, it's always 90 degrees behind the source. For a inductor, it's always 90 degrees ahead for the source, or what we call plus 90. But then if you're asking for the voltage in the actual circuit, that's a whole different thing. And that phase angle is given by phi equals, they normally do the cosine inverse, just because that's a little easier to calculate. But what you're seeing here is you're going to have a vector, and this length would be omega L minus 1 over omega C. And this length would be just R. So in other words, remember V equals IR. Well, V is also equal to IXL, and V is also equal to IXC. So what I've done is taken out the I from in front of each of these, and this right here is the angle phi. So phi equals a cosine inverse, which is adjacent R, over hypotenuse, which is the square root of R squared plus omega L minus 1 over omega C squared square root. And remember, omega is actually 2 pi F. It's not the 60 hertz. It's 2 pi times the 60 hertz or whatever. Did that help you?
Yeah, that makes sense. I admittedly, I did the phaser explain thing, and for some, yeah, you basically yeah. Sorry, I connected the dots, and I feel relatively incompetent, but that's okay.
No, and that's perfectly normal, dude. That's the way it happens in physics. It's like we literally say that problem's intractable, that problem's impossible. I'm not sure we're ever going to solve that problem. And then as soon as we solve it, we say, well, that's a trivial problem. So
yeah.
So what you just did is transferred from an intractable problem to a trivial problem, and that's okay. It just sometimes it's going to click, and then when it clicks, everything's right, and it doesn't, you feel like an idiot.
Honestly, I don't know. I guess oh man, I don't know. I'm doing my best with this class. It's different, I guess, for the online.
Yeah, it's hard for you guys. I'm not sure I could have done this in y'all's spot. So I completely feel for you. The good news is I'm not getting a huge failure rate. And you know, I'd like to say it's because I'm an awesome teacher, but everybody knows that's a lie.
Oh,
It's
geez.
it's probably because I make up a really good system where you guys take a lot of practice tests, or at least most people do. And with a lot of practice tests, you get a lot of practice homeworks, and you might not understand all the concepts right now, but you can at least mostly solve problems. And but to believe it or not, when you first finish a calculus-based physics class or even an algebra-based physics class, it's all about, can you solve problems? 2 years down the road, it's going to become, oh crap, I understand that now. But literally, it might not come for a year or 2 years. I mean, if you're, you know, Stephen Hawking or Witten or somebody like that, it came immediately. Other people know it's going to come, you know, a year later. So don't feel bad. There's nothing wrong with you. You're perfectly normal.
That's good.
Well, have a good one, Sam. You need anything else?
I was curious about if this is the same thing with RC circuits as well, but I mean, it probably is.
Yeah, it is. RC, the good news with RC is you only have the capacitance that's lagging. And normally what happens with that is basically an RC circuit, if you have a DC source, it's just going to charge up the capacitor, then you disconnect it and the capacitor will discharge. If you have an AC source, it's going to act just like this, and it's going to try to cause that lag. But it's not necessarily going to decay quite as bad over time because you're not losing so much energy to the inductance. Remember, every time you send current through an inductor, you're creating a magnetic field. A magnetic field takes an amount of energy equal to 1/2 B squared over mu. And whenever you charge up a capacitor, you're creating an electric field, and electric fields takes energy of 1/2 epsilon 0 E squared. So what you've just done when you're dealing with a RC circuit as opposed to a RLC circuit is you've gotten rid of one of the sources of energy that can be problematic, right? So you maybe get one that runs a little more. Now the dissipative heat is mostly through the R, and of course that's your big heat sink or energy sink, if you will. It's just the pure heat that's going to happen as the resistor gets hotter and hotter before current's going through it. And either I completely made that way worse, or you just like had a eureka moment, and I'm probably leaning towards the former.
It makes relative sense. Admittedly, like what you said earlier is kind of the case where I'm kind of just doing my best to get the problems solved, and I think I understand like the concept of AC in the sense of like the voltage source goes up to a high point because of just the way that the physics works with the orientation of the plates or the inductor. I can see why they lag,
right,
based off of just like conceptualization.
Well, that's most of the battle, just being able to figure out that they should lag at all and why they lag. That's the majority of the battle. I will tell you, one, most students are not reading their textbooks. That's just a general rule. I know I worked really hard to read my textbooks, but I was like literally the only one, even when I got to my junior and senior years. Other than I had a lot of foreign students when I got to grad school, they were reading them, which was amazing because they were reading in the second language. But anyways, most of the students weren't reading their books. And the reason isn't because they're lazy, it's because they feel like it doesn't do them a damn good of good. So if this part's what's bothering you, I would look for way lower level books. Like I have this book on my shelf called Understanding Electronics by Waring, and it's a electronic technician's book that was on sale at Radio Shack. So you can probably find something just like it on the internet that you don't even have to buy. And that makes better physical sense to you than your book will. And then when you read your book will make more sense. So if you're really having a problem with electricity, magnetism, specifically circuits, look for circuit analysis books for technicians, because they see like capacitors as a pump. It's literally like a water pump. And when you start looking at it like that, everything becomes mechanical and it makes perfect sense. So you can give that a try too. They sell these little bulletins. They used to, back before Radio Shack went out of business. They sell these little 10, 20 page things that were, you know, about the size of a pocket notebook. And they just sort of gave you the details and models of what to think of each of these components as, whether it be a transistor or a transformer or a LED or whatever. So look for that. That might help you a lot.
Definitely. I wrote down that book. Just I don't know if it's still around, but I'll it might be a
it's a McGraw-Hill book, so it probably still exists, and it probably at this point it might even illegally be in PDF format for free on the interweb. I say interweb to make myself look old. The interwebs. All right, man.
Thank you so much, Professor.
No problem. Have a good one, Sam. Paul, do you need anything, bud?
Professor, can you hear me?
Yes, I can.
I'm not sure if you received my email about my attendance from the 14th to the 27th.
Yes, I remember getting an email, but I'm trying to refresh my memory now. Let me pull it up real quick.
Okay.
First off, let me stop recording because this might be something personal.
That's fine, Professor. Thank you.
No problem. Like I said, thank you for your service, and don't worry if you have to miss something like that. That's not a big deal. I work with everybody, not just my vets, but I'm definitely going to work with my people that are in the military. So thanks, sir.
All right, cool. Thank you. All right.
Have a good one. Bye.